The Sun, like other stars, is essentially a gigantic fusion reactor. At its core, immense pressure and temperature create an environment where hydrogen atoms collide with such force that they overcome their mutual repulsion and fuse together, forming helium. The Sun doesn't burn in the same way that a fire does here on Earth. Instead of combustion, the Sun produces its energy through a process called nuclear fusion. Let's delve into the details of nuclear fusion and how it powers the Sun. Nuclear fusion doesn't involve oxygen because it's not a chemical reaction. Chemical reactions involve the rearrangement of electrons between atoms, and the Sun is primarily composed of hydrogen, with very little oxygen present. Unlike combustion, which relies on oxygen as an oxidizer to release energy, fusion does not require oxygen. Instead, it relies on the strong nuclear force, which binds protons and neutrons together in the nucleus. The absence of oxygen does not hinder fusion in stars like the Sun because the primary fuel is hydrogen. Chemical combustion. This is the fire we're familiar with. Wood or fuel reacts with oxygen, releasing heat and light. Think of a campfire. The wood combines with oxygen to form carbon dioxide and water vapor, releasing energy as heat and light. Nuclear fusion. In stars like our Sun, the story is entirely different. At its core, under immense pressure, millions of times Earth's atmosphere, and scorching temperatures, millions of degrees Celsius, hydrogen atoms undergo a dramatic transformation. While immense pressure initiates fusion, temperature plays a crucial role. The millions of degrees Celsius within the Sun's core provide the necessary energy for hydrogen atoms to overcome their natural electrical repulsion. Imagine trying to push two like-charged magnets together. It takes a lot of force. The high temperature allows the protons to get close enough for the strong nuclear force to take over and bind them together. Nuclear fusion isn't a single, isolated event. The energy released from one fusion reaction creates even higher temperatures, allowing more hydrogen atoms to overcome repulsion and fuse. This creates a self-sustaining chain reaction that keeps the Sun burning brightly. Energy release mechanisms. The energy released in fusion comes in two primary forms. 1. Gamma rays. The majority of the energy is released as high-energy gamma rays. These gamma rays bounce around within the Sun's core before interacting with other atomic nuclei, transferring their energy and heating the surrounding plasma, a hot, ionized gas, even further. 2. Kinetic energy. A small portion of the energy is released as kinetic energy of the newly formed helium nucleus. This energetic helium core collides with other atoms, further heating the plasma and contributing to the pressure that keeps the fusion process going. Factor affecting sunburns without oxygen. The heat generated by fusion slowly works its way outwards from the Sun's core through a process called radioactive transfer. Photons, particles of light, are constantly absorbed and re-emitted by the surrounding plasma, eventually reaching the Sun's surface and radiating out into space as the sunlight that warms our planet. 1. Proton-proton chain reaction. The main fusion process in the Sun is the proton-proton chain reaction. When two protons, hydrogen nuclei, fuse to form a deuterium nucleus, a proton and a neutron, releasing a positron and a neutrino. A proton collides with the deuterium nucleus, producing a helium-3 nucleus, 2 protons and 1 neutron, and a gamma ray. Overall, the net result is the conversion of 4 hydrogen nuclei, protons, into 1 helium-4 nucleus, along with the release of energy in the form of gamma rays and neutrinos. 2. Energy release. The energy released during these fusion reactions is immense. It's a result of the mass difference between the initial hydrogen nuclei and the final helium nucleus. According to Einstein's famous equation equals 2, this mass difference is converted into energy, whereas energy is mass and is the speed of light. 3. The role of gravity. Gravity plays a crucial role in sustaining the conditions necessary for nuclear fusion in stars. The immense gravitational pressure at the core of the Sun keeps the hydrogen gas compressed, ensuring that temperatures and pressures remain high enough for fusion to occur. 4. Stability and balance. The Sun achieves a delicate balance between the inward gravitational force trying to collapse it and the outward pressure generated by the energy released through fusion reactions. This balance maintains the Sun's stable structure over billions of years. 5. Solar neutrinos. As a byproduct of nuclear fusion in the Sun's core, neutrinos are produced. These are subatomic particles with very little mass and no electrical charge. They can pass through the Sun's dense interior and travel through space at nearly the speed of light, providing valuable information about the fusion processes happening within the Sun. The Sun burns through the process of nuclear fusion, where hydrogen nuclei fuse together to form helium, releasing immense amounts of energy in the process. This process is sustained by the intense pressure and temperature at the Sun's core, which overcome the Coulomb barrier through quantum tunneling. Unlike combustion, which requires oxygen, nuclear fusion relies on the strong nuclear force and operates independently of the presence of oxygen or any other element. In summary, the Sun burns through the process of nuclear fusion, where hydrogen nuclei fuse together to form helium, releasing immense amounts of energy in the process. Unlike combustion, this process doesn't require oxygen. Instead, it relies on the powerful forces within atomic nuclei. Understanding nuclear fusion is not only essential for comprehending the workings of stars like the Sun, but also holds promise for clean and abundant energy generation here on Earth.